biochemical pathway through which a molecule of the 6-carbon sugar, glucose, is converted to 2 molecules of the 3-carbon compound, pyruvate. In this process, free energy is sequestered in the form of 2 ATP molecules. The first reaction of glycolysis is catalyzed by the enzyme hexokinase, which mediates the transfer of ATP's gamma-phosphoryl group to the number 6 carbon of glucose. The reaction occurs through the nucleophilic attack of glucose's 6-hydroxyl group on the gamma-phosphorus atom, yielding glucose 6-phosphate and ADP. This is the first of 2 reactions in which the free energy of ATP hydrolysis is invested in the pathway. The second reaction of glycolysis involves the isomerization of glucose 6-phosphate, an aldose, to fructose 6-phosphate, a ketose. The reaction is catalyzed by phosphoglucose isomerase. In order for the isomerization to take place, the 6-membered glucopyranose ring must first be converted to its linear form. This reaction step is catalyzed by proton donation, probably from a lysine epsilon amino group. An enzyme base, probably a glutamate carboxylate group, abstracts the now acidic proton from C2 to form a cis-enediolate intermediate. The proton is then replaced on C1, forming fructose in its linear form. In the final step of the reaction, the 5-membered fructofuranose ring forms in what is essentially the reverse of the reaction that opened the glucopyranose ring. In the third reaction of glycolysis, a phosphoryl group is transferred from ATP to fructose 6-phosphate by the enzyme phosphofructokinase. This brings the net investment for the pathway to 2 ATPs. The product of the reaction is fructose 1,6-bisphosphate. Phosphofructokinase catalyzes the rate-determining step of the glycolytic pathway. In reaction 4, the enzyme aldolase cleaves the 6-carbon monosaccharide fructose 1,6-bisphosphate into 2 3-carbon molecules, glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Class 1 aldolase binds fructose 1,6-bisphosphate in its linear form as a protonated Schiff base. A tyrosine side chain in its phenolate form then abstracts a proton from the 4-hydroxy group of the substrate. This initiates an aldol cleavage reaction between the substrates number 3 and number 4 carbons to yield 1 molecule of glyceraldehyde 3-phosphate and an enamine intermediate. The reaction is catalyzed because the electron pair that formed the cleaved bond is readily delocalized by the protonated Schiff base to form the enamine. The glyceraldehyde 3-phosphate is released by the enzyme and proceeds along the glycolytic pathway. The enamine is protonated by the tyrosine side chain, and the resulting iminium cation is hydrolyzed to yield the reaction's second product, dihydroxyacetone phosphate. The fifth reaction of the glycolysis pathway, catalyzed by triose phosphate isomerase, is the isomerization of a dihydroxyacetone phosphate to glyceraldehyde 3-phosphate. In this reaction, the carboxylate group of a glutamate residue, acting as a general base, abstracts a proton from carbon atom 1 of dihydroxyacetone phosphate, while a histidine side chain, acting as a general acid, protonates the carbonyl oxygen at position 2, thus yielding an enediol intermediate. The glutamate side chain then donates its previously acquired proton to carbon atom 2 of the enediol intermediate, while the histidine side chain abstracts a proton from the hydroxyl group at position 1, to yield the product of the reaction, glyceraldehyde 3-phosphate. At this stage of glycolysis, the original glucose molecule has been converted to two glyceraldehyde 3-phosphate molecules. Although we will see only one molecule of glyceraldehyde 3-phosphate reacting here, keep in mind that two of these molecules will actually be reacting in the biological pathway for each glucose molecule that entered it. In the sixth reaction of glycolysis, the enzyme glyceraldehyde 3-phosphate dehydrogenase catalyzes the oxidative addition of a phosphate group to glyceraldehyde 3-phosphate. The reaction begins with the nucleophilic attack of an enzyme sulfhydryl group on the substrate's carbonyl carbon to yield a thiohemiacetal intermediate. This intermediate is then oxidized by the direct transfer of a hydride ion to NAD to yield NADH and an acyl thioester intermediate. The NADH product is replaced by NAD. Then, inorganic phosphate nucleophilically attacks the carbonyl carbon of the acyl thioester intermediate to yield the reaction product 1,3-bisphosphoglycerate and regenerating the active enzyme. Reaction 7 is the first reaction of glycolysis in which free energy is recovered. In this reaction, the synthesis of ATP is driven by the high negative free energy of hydrolysis of the 1,3-bisphosphoglycerate's acyl phosphate. This reaction is catalyzed by the enzyme phosphoglycerate kinase and occurs by the nucleophilic attack of ADP's terminal phosphoryl group on the C1 phosphoryl group of 1,3-bisphosphoglycerate to yield 3-phosphoglycerate and ATP. Since two molecules of ATP are generated for each glucose molecule that entered the pathway, this brings the net ATP yield of the pathway at this stage to 0. In reaction 8, the enzyme phosphoglycerate mutase catalyzes the transfer of a phosphoryl group from 3-phosphoglycerate's 3 position to its 2 position, yielding 2-phosphoglycerate. The active enzyme contains a phosphohistidine residue. The reaction begins when the enzyme transfers this phosphoryl group to 3-phosphoglycerate's 2 position, yielding 2,3-bisphosphoglycerate, which remains bound to the enzyme. The phosphoryl group at position 3 of this intermediate is then transferred to the histidine side chain, yielding the reaction product 2-phosphoglycerate and regenerating the active enzyme. In reaction 9, the enzyme enolase catalyzes a dehydration that converts 2-phosphoglycerate to phosphoenol pyruvate. Reaction 10, the final reaction of glycolysis, is the pathway's second reaction in which free energy is recovered in the form of ATP. Here the synthesis of ATP is driven by the high negative free energy of hydrolysis of phosphoenol pyruvate. In the first step of this reaction, a phosphoryl group is transferred from phosphoenol pyruvate to ADP to form enol pyruvate and ATP. The enol pyruvate intermediate then tautomerizes to form the reaction product pyruvate. It is this highly exergonic tautomerization that provides the free energy to drive the formation of ATP. Again, as two of these reactions occur for every glucose molecule that enters glycolysis, the yield of ATP for this reaction is 2 ATP